In this lesson, we're going to take a look at complex roots of quadratic and cubic functions. So let's start off with an example. So we'll take an example of a quadratic. So let's say the function is f of z is equal to z squared minus 6z plus 13. We normally use fx in algebra, but when it's a complex number, we use z normally. That's the only difference here so far. Now, we need the roots, so that means when it's equal to naught, what are the values of z? So you put z squared minus 6z plus 13 equal to 0. And there are no factors of this, so we use the minus b formula just as if it was x's. So we'll just use the minus b formula here, where a is 1. So it's 1 z squared. So that's a, that's b, and that's c. So a, b, and c. Obviously, don't forget to take the minus with you as well. So z is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. And that gives us minus 6, which is plus 6, plus or minus the square root of 6 squared, which is minus 6 squared, which is plus 36, minus 4ac, which is 4 by 1 by 13. All over 2a, which is just 2. So that's 6 plus or minus the root of 36 minus 52 over 2, which is 6 plus or minus the root of, that's minus 16. Be careful there, that's a minus 16 because it's 36 minus 52 over 2. Now we can split that into 6 plus or minus the root of minus 1 by plus 16. Just get factors. And now we can break those up. So it's the root of minus 1 by the root of 16 all over 2. And the root of minus 1, of course, has a special value. That's the imaginary number I. So we now have 6 plus or minus I by root 16, which is 4. And finally, 2 divides unevenly, so 2 into 6 goes 3 times, plus or minus 2 into 4 goes 2, so it's 2i. So just to summarize what happened there, if you have f of z is equal to z squared minus 6z plus 13, well, the roots of that are z equals 3 plus or minus 2i. So a few things to notice there. It's the exact same method as we use in algebra for x's. Even back in junior cycle, all you ever did was use, if there was no particular factors, easy factors to work out, you just use the minus b formula. It's the same here. It's just in junior cycle, you never ended up with a minus under the root. It was always a plus number. So when there's a minus, we just have to handle it a bit differently from here on. We just have to call it I. And that's the big thing that's different there. Now, the other thing I want you to notice is you'll notice that the roots are actually conjugates of each other. So that's z is equal to 3 plus 2i, or z is equal to 3 minus 2i. So you'll notice when you factorize a quadratic that has a minus under the root, the roots are conjugates of each other. That's what a conjugate is when the sign of the I changes, of the I part changes. So this is something that's going to be important in a few minutes. The fact that whenever you've got a quadratic like this, the roots occur as what's called a conjugate pair. So we'll just make a note of that. They are a conjugate pair. Okay, so that's the first part done. Now the second part is we're going to do that process now in reverse. Let us say that you just knew the roots. Okay, so we started with a polynomial up here, and we ended up with 2 roots. Can we not do that in reverse? If you have 2 roots, can you end up back with the polynomial up here? And so that's what we're going to do next. We're going to start off with the answer and work backwards to the question, as it were. Do all these steps in reverse. So on the next page, I'm going to do that. So z is equal to, so if I say the roots are, z is equal to 3 plus 2i or 3 minus 2i. And we need to go backwards now and get the actual polynomial, which is what this is called, by the way. That's a quadratic polynomial, what we started off with. So that's what's called a polynomial. Poly for many, nomial for numbers. So many numbers, when the z's go down in sequence like that, the powers go down, it's called a polynomial. To be precise, this is a quadratic polynomial, as opposed to, for example, a cubic polynomial, or any of the other powers. So we want to go basically back from roots to a polynomial. Now, it turns out that there is a very useful formula for doing this. If we go back to algebra for a sec, let's forget about complex numbers, just go back to algebra. And just for a few minutes here, let's forget about the question we're doing. I want to just do something on the side here that will help us. So you take a polynomial like x squared plus 7x plus 10, for example. What are the factors of that? Well, if you open two brackets, the factors are x and x, 5 and 2. So that's a plus and a plus. And finally, you can get roots. So that's, x, when you put it equal to 0, x plus 2 equals 0, or x plus 5 equals 0. So x equals minus 2, or x equals minus 5. So when you start off with a polynomial, you go from polynomial to factors, and you go from factors to roots. There's 3 steps involved. And you can see the connection here. You might spot a connection now between the roots and the original polynomial. If you look at, actually, we make it more specific, we'll just put the yellow on the number itself. So we'll just highlight the number and see if you can spot a connection here with the 7 and the 10. And what you'll spot is, if you add your 2 roots, minus 2 and minus 7, so the sum of the 2 roots, minus 2 and minus 5 gives you minus 7. And the product, if you multiply them, if you get minus 2 multiplied by minus 5, you get plus 10. And you'll notice that the sum is basically the number in front of x in the polynomial, except the sign has changed. And you'll notice the product is the number on its own there. So if you want to go backwards, in other words, all you have to do ever is, if I just say backwards here, all you ever have to do is go x squared minus the sum, you change the sign of the sum, times x plus the product equals 0. So x squared minus, now the sum in our case is minus 7, x plus product is 10 equals 0. So that's x squared, let's get rid of this now. So that's x squared plus 7x plus 10 equals 0. And we're back to where we started, as you can see. So that's exactly where we started with the polynomial. So polynomial to factors to roots, that's going forward. And then in reverse, when you start off with the roots, it's x squared minus the sum of your roots and plus the product equals 0. And you're back to your polynomial. So this is a very powerful formula for going backwards. When you have the roots and you want to go backwards to get the polynomial, you use this formula. So back to here then, it's the same thing over here. Don't let the z's put you off. It's the same basic idea. So you get this, these are your 2 roots. Recall what we're trying to do. We're trying to go backwards. You see, we had the polynomial to start off, and that gave us the roots when we used the minus b formula. Now let's pretend that we never saw the polynomial, and we're trying to get it from the roots here. So we're trying to end up with that from these 2 roots. So now we can just use that formula. The formula is z squared minus the sum times z plus the product equals 0. So let's do that then. The sum is 3 plus 2i and 3 minus 2i. The two i's cancel and 3 is 6, so the sum is 6. Now the product is easy as well, because the product is just 3 plus 2i by 3 minus 2i. You might recognize that as a formula, difference of two squares, x plus y by x minus y. And that's a formula in algebra, and the answer is x squared minus y squared. So it's 3 squared minus what's y? Y is the 2i to be squared. If you're not confident using that method, you can just multiply out the brackets the long way if you want. That's okay as well. But when you do that, you get 3 squared is 9 minus 2 squared is 4i squared, which is 9 minus 4 by minus 1, because I squared is minus 1. So it's 9 plus 4, which is 13. So we have the sum and we have the product, and now it's just a matter of filling in the formula. So if you fill in this formula here, what do we get? So if you fill in the formula, you have z squared minus sum. Well, the sum is 6 z plus the product, which is 13, equals 0. And as you can see, we're back to where we started. That's the polynomial. That was the original formula that we started off with. Z squared minus 6z plus 13. Let's just check our answer. There it is. Z squared minus 6z plus 13. So just to summarize, what we've done so far today is going forwards and backwards. Going forwards means going from polynomial to roots and here. And going backwards means, on the next page, going from roots to polynomial. Roots here to polynomial down here. And I've put some algebra on the side there on the right to remind you of this section in your algebra section of your course. So that's over here in a separate section. Now we'll just take it one step further before we finish. We've talked now about quadratics. Now let's go on to cubics. So that was a quadratic polynomial. Now let's go on to a cubic polynomial. So cubic polynomials. With complex roots. So let's try and let's have a look at this. So take an example again. Find the roots of z cubed minus 7z squared. Actually, maybe just give it a name as well, call it f of z. So just give the polynomial a name. So this function is z cubed minus 7z squared plus 19z minus 13. So find the roots of that. Now, given that we'll give you one of the roots. So for example, one of the roots would be, actually this ties in with the last one, so it would be 3 plus 2i is one root. Now, so to tackle this question, we have to spot a few things here as well. And the first thing to spot is that it's a cubic. I mean, we saw earlier that a quadratic has 2 roots or 2 factors. So if this is cubic, it's going to have 3 roots, 3 factors. So there are 3 factors here. So if you like, there's going to be z minus something by z minus something, z minus something. Think about your 3 factors. Z by z by z is z, gives you the z cubed part. So, and there's obviously some other factors here as well, some other parts to the factors. Now, of course, taking 2 together, those 2 together give you quadratic. And what we know about quadratic from the last section is that in a quadratic, the roots occur in pairs. Now, we already have one root. It's 3 plus 2i. We're given that. So 3 plus 2i is one root. So that's a root of one of those. So if that's a root, well, we know from the last section that they occur in conjugate pairs. If we go back for a sec, we saw that the roots occurred in any quadratic in conjugate pairs. So if 3 plus 2i is a root, well, 3 minus 2i is the other root automatically. Of course, that works as long as the coefficients here, the numbers a, b, and c, are real numbers. As long as they're normal numbers, you'll get conjugate pairs here. So that's straight away we've got one root without hardly trying, because if you're given one, which you often are in a question, 3 plus 2i, well then automatically its conjugate is also a root. Without even working it out, you can be sure that 3 minus 2i is also a root. So there's the second one, 3 minus 2i. 3 minus 2i is also a root. That's the conjugate. Now, if they are roots, can we get the third one is the question. Can we get the third root? And so this is the last part of it now. So again, just to remind ourselves that roots and factors are two sides of the same coin. So going back to the quadratic again for a sec, we saw that, for example, if you have a factor here, x plus 2, well, the root is x equals minus 2. So if the factor is a plus, the root is a minus, and vice versa. That's basically what's called the factored theorem. So they go. If you have one side of the coin, you have the other. Factor is x plus 2, root is x equals minus 2. Now back here, use the same logic. If the roots are z equals 3 plus 2i and z equals 3 minus 2i, well, then the factors are, you just change the sign. Z minus that, minus 3 plus 2i, and z minus 3 minus 2i. In the same way, again, we have to remind you of this one more time. I mean, if you had x equals 2, x equals minus 2 are roots, for example. So this is rough work here. Well, then x minus 2 by x plus 2 are factors. That's just what's called the factored theorem. That's all it is, the factored theorem. And that's all I'm using here. Except the root itself looks a bit more awkward. I mean, instead of 3 plus 2i here, which is the root, I only have 2 here, for example. Instead of 3 minus 2i here, I only have minus 2. So what happens to that? You can see there that the 2 went to a minus 2 inside the bracket. So the 3 plus, that's the 2 there. So the 3 plus 2i goes to minus 3 plus 2i inside the bracket. So we can put a bracket around that, I suppose. And the same here. The 3 minus 2i goes to minus 3 minus 2i when it's a factor. Now, so when you multiply those factors together, then, when you multiply these two factors together, you get a quadratic, which is part of the overall cubic. Then there's just one more factor to work out after that. So let's just work out the quadratic part now by multiplying these two factors together. So we have z minus 3 plus 2y multiplied by z minus 3 minus 2y. And what do you get? Well, you get, let's tidy it up, z minus 3 minus 2y, get rid of the inside bracket. And here, z minus 3 plus 2y. Now, that looks messy enough to multiply out because there's 3 terms in each bracket, but again, there's a shortcut, and the shortcut is this. If you spot that that's z minus 3 is all one thing, and we can spot that, for example, 2y is something else. So it's now a green thing minus a yellow thing, if you want to say it that way. So it's x minus y again by x plus y. So now we've got a shortcut. So now we got a shortcut, and so now it's just the formula again. It's x squared minus y squared. So it's x squared minus y squared is the answer. So it's the green thing squared minus the yellow thing squared. Now z minus 3 in a bracket square out the bracket. It's z squared minus 2 3s is 6 by z plus 3 3s is 9. Square out the bracket the long way if you want. Minus 2i by 2i is 4i squared. 4i squared. And now we've got z squared minus 6z plus 9. Minus I squared is minus 1, so it's minus 4 into minus 1, which is minus 4 by minus 1, which is z squared minus 6z minus minus is plus, so plus it's plus 13. So now we have that quadratic part, and don't forget the big picture. The three of them together, that by that by that, gives us the overall polynomial. So we have 2/3 of it now. We have the quadratic part. So now it's just a matter of the missing part multiplied by this gives us the cubic, or the other way around. You could all equally say that the quadratic divided into the polynomial gives us the remaining factor. I mean, it's like if you had 2 into 12 goes 6 times, but 2 by 6 is 12 as well. It's the same thing up here. So basically I have a factor multiplied by a quadratic equals the cubic. So if I basically divide the quadratic into the cubic, I get the last factor. And that's what we want to get the last root as well. So this is just rough work again here to show you what we're doing overall. So now let's do our long division. So it's z squared minus 6z plus 13, and divide that into the original polynomial, which was up here z cubed minus 7z minus 7z squared plus 19z minus 30. So let's go with that, and z squared into z cubed goes z times. Z by z squared is z cubed minus 6z squared plus 13z. Now draw a line, change the sign. That's minus, that's plus, that's a minus, and now we get the z cubes cancel. That's a minus a z squared, that's 19 minus 13 is 6 plus 6z, and bring down the minus 13 over here. And one last time then z squared goes into that minus 1 times, so it's minus z squared minus 1 by minus 6 is plus 6z plus minus 13. You draw a line, change the sign, and of course you get 0, which is what you want. There's no remainder, so it divides in evenly, and that means that the other factor is z minus 1. Now if z minus 1 is a factor, well, that means that z equals 1 is the root because of the factored theorem. And that's the last remaining root. So we have our 3 roots now of the polynomial. What was the original question? The original question was, given this polynomial f of z up here, can you find the 3 roots? Well, we were given 1, 3 plus 2y. So because of that, we have the other one automatically because it's the conjugate, 3 minus 2y. And lastly, then, we got the third root, which is z equals 1. And that's the end of that lesson.